Um, so yeah, hi, and welcome everyone, and thank you for joining us for our first webinar for the STFC Batteries Network. So I'll start off with some house rules. So yeah, throughout the presentation, you can type your questions in the Q&A box, and I'll keep an eye on that, and I'll ask Sam your questions. And then, yeah, also this webinar is going to be recorded. If you also notice, there's a poll. So if you guys could answer the questions in the poll, that would be really appreciated. It's anonymous as well. So yeah, I hope you really enjoy our first webinar today, presented by Sam Cooper. So Sam is a lecturer at the Dyson School of Design Engineering and a member of the Electrochemical Science and Engineering Group at Imperial College, London. His work is primarily focused on the design of next generation energy storage technologies, as well as exploring the use of machine learning in his approaches. So yeah, and Sam is also my neighbor, which is great. So his webinar is entitled Pause for Thought, Designing Electrode Microstructures Using Machine Learning and Reflections on My Early Career. So yeah, I'll now give the floor to Sam. So Sam, go ahead when you're ready, please.
Thanks, Rema. Can you hear and see me okay? And you can see the slides okay?
Yeah.
Excellent. So hello all. Thank you all so much for joining me this afternoon. All 175 of you, my God. My name is Sam Cooper. As Rema said, I'm at Imperial College in the Dyson School. And I'm going to share with you first some insights about my experience of being an early career researcher and some tips, I guess, about how I think I would best go about doing that. And then I'll share with you two exciting new papers in the space of microstructural analysis for electrochemical devices. So first, by way of introduction, I'm actually not on my own at Imperial. I'm part of a consortium of academics, and we work together across a very wide range of technologies, including everything from sort of microscale, nanoscale, all the way up to techno-economics at the very top. And that includes 8 academics with nearly 80 PhD students and postdocs. So it's a huge team effort spanning multiple departments. And I think that's a hugely beneficial way of doing things, because we end up having conversations that I think if you just left me on my own with tortuosity, I'd probably be perfectly happy, but it's quite useful to have someone a few length scales up say, what's the point of that every now and again. So here's the prettiest picture I could find of Imperial College. For those of you who haven't been, it's this bit. And I have been here for, this is my 12th year on this campus. And so I'm pretty institutionalized. So I started off in the mechanical engineering department, and I was living in this building here, one of the student accommodations. And then I moved eventually to do a PhD in the materials department, and then a postdoc in the earth science department, and now I'm in the Dyson School. So you can see I really haven't branched out an awful lot. So I don't want to pretend that I can offer you some kind of years of experience all across vast swathes of academia. It's just not true. However, I am in a new department and a new category of department that many of you won't have necessarily heard of. This is the Dyson School of Design Engineering. It's on the Imperial campus, as you just saw, and it's a lovely old building. And just in the background here, if you look with a laser pointer, that's the back of the Natural History Museum, because this is before the Science Museum was built. And this building is a post office, was the post office. And this is what it looks like now. Much the same on the outside, but totally renovated on the inside. And it's an absolutely fabulous space. We're part of the Faculty of Engineering, and we do a sort of technology innovation focused degree, which means our students, and I sort of wish I'd done a degree like this myself, our students spend a lot of time actually making stuff rather than just thinking about it, which is great to be a part of, great to supervise, which means the degree is mostly coursework, and we are now a proper fully fledged department with sort of 300 students, 70 PhDs-ish and about 30 academics. So we're there. Please, if you ever come to Imperial, come visit us. And I'm going to share now my actual career path itself chronologically. And it actually all kicked off with, while doing my degree, it kicked off with a master's, a summer project, an undergraduate summer project. And rather than actually picking a project that I was interested in, because I didn't particularly know I was interested in energy at the time, there are lots of interesting topics around, I just picked my favorite lecturer. So the person I wanted to work with most, and I approached him and he said, we don't have a project. And I said, well, can you make one? And so we found some money and we made one, and that was great fun. And then through Fred, I met Paul, and Paul was my co-supervisor for my master's project, and Paul showed me why the simulation work I've been working on could be really useful for energy materials. And one of my key stories for Paul about that time was that he came in one day, I think this was just after I'd started my PhD, and said, right, we want to publish a paper based on some of the work that you've done. And I said, great, you know, how does that work? And he said, oh, well, we just sit down right now. So he got his laptop out and we sat down for, I think, 5 hours, and we just wrote a paper, and then we sent it around to all our collaborators. And it was pretty exhilarating and absolutely exhausting, but you know, a really kind of big distinction from how I thought the process would necessarily run, right? And I certainly haven't done that again since, but it was quite an exciting moment at the time. Then I moved on to a PhD with John Kilner in the materials department, and John was of the frame of mind, or of the view, that I could pretty much do whatever I wanted. And so this meant a lot of worry at the start of my PhD. So if you're at the start of your PhD now, or thinking about doing a PhD, there will be very likely a lot of uncertainty at the start. And I think that's quite an important part of the process. And I actually spent the first 8 months of my PhD building a high temperature in situ rig for imaging fuel cells while they are running. And that didn't feature a single word in my thesis about this, but it allowed me to explore this space. It forced me to ask myself which things matter, which things don't matter. And there was a lot of the skills that I learned from doing that translated to the work along the way. Then, coming to the end of my PhD, we were lucky enough to have a Marie Curie fellow come and join the group, Dr. Antonio Barte, who's now at Pisa. And he was an absolute champion in forcing me to produce high quality stuff. He absolutely is one of those people that will not put up with anything but the best. And so this was a really good experience for me to have someone like Antonio come along and say, look, you need to focus on this, this, and this. And then Nigel took me on for a postdoc. And the great thing with Nigel is he would put me in front of an audience as often as possible. So, you know, gets invited to meetings all the time, and he'd say, right, no, Sam, you're going to this one, you're doing this meeting. And that, often nerve-wracking, but was actually a really great experience. The other thing that Nigel did, which was great, is underwrote a lot of my ideas. So I'd have an idea, like I want to organize a conference or something. And Nigel would say, great, get on with it, and we'll work out where the money's going to come from later. And we'd always find a way to get some money. Yeah, having that confidence behind you, having someone backing you and saying, yeah, just go for it, was absolutely glorious. And then Billy, who is basically Mr. Motivator, who throughout the process, and especially towards the start of my application process for lectureships, would just constantly encourage me to apply for stuff. And I think it's very important to have a Billy in your life. If you can find one, it's very helpful. Someone who will just keep encouraging you to apply for things and put yourself out there. So now I am a lecturer in the Dyson School, and it's all led to this point, which is the invited talk for the beginning of the STFC seminar series. So thank you so much, Rema, for inviting me along. So before I talk about the actual research bits, I would like to offer my tips about, based on my experiences as an early career researcher, things that I think were really beneficial, things that looking back were a really good use of my time. I think number one for that is to organize things, right? I chaired our group meetings. It's a small job, but actually it gives you a flavor for what it's like to try and wrangle people and get them to be in the same place at the same time, watching the same lecture. I even set up a series of informal group meetings because we wanted to have a different style of conversation without the pressure of having the professors watching us. I got stuck with maths, went and bothered a bunch of mathematicians, and that was really helpful. So I set up the Maths Help Desk, which is a campus-wide initiative where anyone can email saying I'm stuck with a maths research problem, and they'll be triaged and put in touch with maths PhD students. And then I've organized a selection of conferences, including ECRC, which this series is replacing, or which this series is standing in for, and IC3D, which is an Imperial College three-dimensional imaging conference. And that was entirely my own baby. And it, you know, left me a lot of freedom to think, well, how can you really do things differently? How can you do things in an interesting way that will, you know, get an exciting response from the audience? And so one of the, it's a tiny little thing, but one of the things I did is made sure that everyone's imaging particle of choice and everyone's length scale of choice was written on their badge at the conference so that they could more easily strike up conversations with other people. And that seemed to work quite nicely. The next tip is teach. For those of you who know me well, you'll know that I absolutely adore teaching, and I spend a lot of my time doing it. These are all clips from an online course I released about 2 years ago, which is teaching the mathematics of machine learning. And the reason I think teaching is so important is not just because, you know, it is good to share your learnings with other people, but my goodness, does it force you to learn the stuff yourself. And so this course is actually, often it's the basics, but nothing really forces you to make sure that you actually know the basics, like trying to teach the basics to someone else. And so whenever I get the opportunity, I'll try and teach some new topics to try and push myself to really get to grips with it. So at the moment, I've got a seminar series with my team and a bunch of other PhD students where we're walking through the maths of impedance, which is a famously mysterious topic. And there are a range of other, you know, topics that I've got seminar series for CETs that I just love to deliver. It's great fun. The next one is make software, not code. So this is my collaborator, Matt, during my PhD. And it's one thing to write a bunch of code that solves a problem. But in principle, you'd like people to use that code. And lots of people don't spend all of their time coding like I do. They might spend their time trying to work out how to do very fiddly experiments. So if you'd like people to use your code, make sure it's usable. And, you know, at least make sure it's clean code, but at best, turn it into a little software package. It is an investment of time, but I found it immensely rewarding. And it forces you to write code in a way that makes it robust, makes it not constantly spit out errors that you ignore and try and run past, but makes it so that someone who doesn't code, but does do experiments and collect data, can use and can really benefit from. And I absolutely love that. The next tip is to publish your software. If you've gone to all that effort, don't just leave your software wallowing somewhere. And this is a nice sort of logical progression. Make some code, make it usable by collaborators, and then put it out there in the world to try and breed collaborations. So I published some software that calculates the tortuosity factor as well as a range of other microstructural metrics during my PhD. And that has led to so many great fun collaborations from all around the world. It's also led to lots of citations, which is very nice. And I can reveal today that we're going to be launching Cow Factor version 2 in about a month's time. And it's faster and it's got a load of tricks up its sleeve that you haven't seen before. And we'll be publishing a selection of papers that talk about each of those tricks. But it's, again, I can't tell you how delightful it is to have a cold call email from someone who says, I'm using your software to solve this interesting problem and I would like it to do this interesting thing, or I found it useful. It's such a joy. So making that effort to turn your software into code, turning your code into software and turn your software into a publication that gets out there in the world is, I think, immensely worthwhile. So here's some of the new tricks that it does, including reproducing various effects that you might see in impedance spectra. And I think that's one of the things for people in the simulation space is to, you know, walk as far as you can towards the experimentalists. So, you know, if you're calculating these results, well, how great if you can export those results in a way that looks like the experimental data that your colleagues are collecting, because then you can start to draw really or have those really interesting discussions where you say, maybe this is what's going on, and that's the whole point. Last tip, tip number 5, this one weird trick doctors don't want you to know, and it's tell people about your work. right? And I've had this conversation with so many people, and it draws very mixed responses. When I publish a paper and I really like it, I will probably email 30 people, and I will spend an afternoon writing a custom email to each one saying, hey, read your work on this and this, saw this paper, noticed you used this. I've just written a paper. It does a similar thing, but with a twist, or, you know, we've got a new method that you can use. Let me know if you'd like to chat about it, right? Because I think it's absolutely bananas to spend a year or more working on some research, you know, really putting in a huge amount of effort to do some research. And then maybe 6 months writing it up, submitting it to journals, getting it accepted, getting it drafted, getting it out into the actual world. And then just to cross your fingers and hope that the right people see it. You know, we all know that there is now a wash of literature. There's constantly more papers than you could possibly hope to read in a lifetime coming out every day. So you should take fate into your own hands, as it were, right? Send it to the right people. If you think this guy at this other university should read it, send it to him and say, read this paper. Because otherwise they might not, and they might miss out on all of the fabulous work that you put in. So, you know, I think some people think, oh God, isn't that a bit embarrassing sending your work? No, just send it. I mean, I don't find it embarrassing. Maybe some other people do, but just send it to people. Okay, so that's the sort of slightly rambly insights into my early career. And I'm now going to talk about some recent papers published. But Rema is just going to drop in a few questions, I think, in this little
yeah, possible. So we had a couple of questions, one question submitted to us before, and so it's what advice would you give to a first year PhD student, and specifically on how to make collaborations as a PhD student?
Right. So, I mean, I think one of the key things, and I kind of alluded to it earlier, is to follow your curiosity, right? You have a fair amount of time in your first year of your PhD. So go off and learn things, right? Dive in. I did a couple of online courses during the first year of my PhD. In fact, I did some on coding and some on data science. I didn't really know how to code when I finished my undergrad. I mean, I knew the basics, but it was actually during my PhD first year where I did some online courses and did some other sort of, you know, followed some textbooks, where I just thought, I actually just really enjoy this. And it wasn't obviously related to the work I was doing. I just did it because I thought it was fascinating and I knew it could in principle be useful. So I think, yeah, certainly in the first year of your PhD studentship, investing some time in just doing things that you think are awesome is great, right? Time gets a bit short later on in your studies, but certainly in the first year.
And like, how would you form collaborations as a PhD student?
I think, yeah, collaborations are so important, and I'm going to be talking about people all the way through this presentation today. I've been so blessed with all the helpful people along the way, and some of which were collaborations. And I think the key thing, the way I go about it, is I just go and talk to people. And I know that's not easy for everyone, and I'm a bit of a loudmouth. But for example, with the software that I use to fit secondary ion mass spectrometry data, I just noticed while chatting to people at lunch that lots of people were analyzing data, but they were all doing it in their own spreadsheet, in their own way, probably doing it all a little bit differently. And so I thought, oh, great, you know, what an opportunity for a collaboration. So I'd reach out to them and say, look, you know, I've got this thought, what do you want to do? I think not being worried about people saying no. I mean, I guess that applies to so many things in life, but just saying, you know, what do you think about this? I think in the first year of your PhD, I think the other thing is, don't be worried about just contacting people. At any stage in your career, if you find a paper interesting and have some questions, email the authors, right? I'm still constantly delighted whenever anyone emails me saying, I've read your paper, I've got this question. Great, you read my paper, I'm so flattered. So yeah, just reach out to people.
Yeah, that's really amazing. Like, I think emailing people has also worked for me, like just out of the blue. I read your one. That's it. Yeah, another question. So would you encourage experimentalists to seek out mathematicians?
Oh, absolutely. Yeah, I mean, I really think, you know, encouraging experimentalists to work, to seek out theoreticians in general, yeah, go and find them. My sort of most fun collaboration in this regard is with Ainara Agudero in the materials department. And she's like a super hardcore solid state chemistry person and knows so much that I've got absolutely no idea about. But I really like the maths and the theory side, and that's not her background. So we have endless conversations about possible experiments that we could design, because if you're all on the experimental side, your space of possible experiments is a bit constrained by things that you think you could fit an equation to. Whereas I might be able to give you some new equations that you didn't know that you could extract data from. So I think that collaboration between experimentalists and theoreticians is so important to make an effort to create.
Cool. And maybe one more question, because then there's some scientific.
Yeah, okay.
Well, so how would you like cope with burnout or getting tired during your PhD? Like,
it's a great question. It's a great question right now. I don't know about anyone else, but I'm finding this particular scenario to be quite exhausting and quite challenging to separate work from other things. It just sort of bleeds into the rest of the day. But I think, weirdly, being strict with yourself, I know it doesn't sound very friendly, but I had every single one of the key ideas in my thesis. There are 5 key ideas in my thesis. Every single one of them I had not in the office. I had it on a train to go somewhere to hang out with friends for a weekend. I had it on a plane to go, you know, on holiday with my partner. You know, perhaps terribly annoying for everyone else around me. But when you change your context, when you force yourself to have a break and go and do something else and lift your head up a bit, I think, you know, for me, that's when I find inspiration to look at things in a different way. And that it's so easy to get stuck down the rabbit hole of your particular problem, where actually you might be solving a problem that no one cares about, or you might be finding a solution in a way that isn't useful. So yeah, I think burnout is actually partially resolved by forcing yourself to take proper breaks, right? And actually they can really help with your work as well. So it's a really virtuous cycle.
cool.
Cool. Shall I press on? I'm happy to stay as long as you want afterwards and answer all these questions.
I think the questions are becoming technical now as well.
Yeah.
So
And the question about machine learning, we're going to get there. We're coming to that.
Cool.
Okay. Right. So this picture has been nabbed from a recent Nature Comms paper from the UCL team, from the EIL team. And it's a lovely combination of images that show you what's going on inside a battery. And of course, the answer is lots. There's lots and lots of things going on. It's a very complicated geometry for a start, but also there's so many different processes going on that interact with that geometry in lots of very challenging to understand ways. So how do I interact with this space? I would like to talk to you about a new paper. So this is my fabulous student, Andrea Gayon Lombardo, and we have recently published a paper, Pause for Thought, Generative Adversarial Networks for Stochastic Reconstruction of 3D Multi-Phase Electrode Microstructures with Periodic Boundaries. What on earth does that mean? Let me tell you. So the key thing, I'm just going to do a micro introduction to some concepts in machine learning. And the point of this is to demystify, right? This is the aim of the game with machine learning is that it's a whole lot easier than electrochemistry. Electrochemistry is really hard. Lots of prior knowledge required, really hard to even get started. Machine learning, easy to get started, quite hard to do well, but easy to get started. And so that's why I think it's generated so much enthusiasm. Right, here's a neural network. You've seen diagrams like this all the time. It's just a function. A bunch of inputs come in and a bunch of outputs go out, right? And that's it. It's a deterministic function. You just put in some numbers and some numbers come out. You put those same numbers in again, you'll get the same numbers out. The magic is not in the object itself. The powerful bit is the fact that we choose functions that are particularly easy to train. So hidden amongst all of these cables here connecting our neurons together are parameters. And just like in an electrochemical model where you've got lots of parameters, here you've got lots of parameters and it strings together, attaches together lots of functions. And that allows you to build a complex representation, a complicated function out of lots of comparatively simple pieces. And that's why machine learning is, or one of the reasons that machine learning has been so explosively adopted, because actually the pieces are quite simple. The interesting bits and the complexity emerges by having lots of it and fast computers training it. Next question from the title, what is a generative adversarial network? Okay, and these things are so cool, and we've spent the last 18 months playing with them, and they only existed for less than 5 years, right? Let me give you a quick story to explain them. So imagine one example of a neural network could be that the input is a photograph of some money. It's a photograph of some money, and the neural network's job is to look at that photograph, okay, to take all the pixel intensities in of that photograph and to give you an output. And that output is real or fake. So if it's real, it's a 1, and if it's fake, it's a 0, but it could be a bit uncertain. So it might be sort of 0.1. So it's probably fake, but I'm not totally sure. Okay, that is just a conventional, you know, feed-forward neural network, right? Can do that. The thing I just showed you on the previous slide. The cool thing with a GAN, generative adversarial network, is you also make a neural network that's kind of like the other way around. So you give it a small amount of information and it blows it up into an object of your choosing. What I do with my generator is I train it, I give it a little bit of random noise, and it builds a picture of some money. So its job is I give it some randomness and it creates for me an instance, an example of a picture of money. And what it's trying to do with that picture is fool the detective. Okay, so the detective's job is constantly to look at pictures of money and say which ones are real and which ones are fake. And the criminal's job, the generator's job, is to try and build fake pictures of money that fool the detective. Okay, and I get to be a sort of spy who goes between them, and I keep telling them whether they got it right or wrong. And so I keep them locked in this game, and they train each other. Right, the spy gets trained by looking at the fake money and getting told by me whether it's fake or not. And the criminal gets trained by looking at by trying to trick the detective, and I tell him what was the outcome of that particular example. Here is the same thing but done for microstructure. So we've got a bunch of training data, some lovely tomography data taken from maybe UCL, and I give it some training data and I train my detective, which looks at that and gives me an output, yes or no. Here's my generator. I give it a bit of random noise and it generates for me an instance of microstructure, which I also then feed to my generator and say, look to my discriminator and say, is this real or not? And then I put it in an algorithm and I make them battle each other until they both get really good at that task. And in the end, this bit is old news. This bit's not very difficult. I can chuck that bit away. But this piece here is a really clever piece of kit. I've now built a function, right? And this it's quite hard to get your head around. I still struggle. It is a deterministic function. It's a function. You give it an input and it gives you an output. That I give it some random numbers and it generates me microstructure as much as I want. Okay, it's a very strange function indeed. So in order to try this out, we took 2 quite different instances of microstructure, examples of microstructure. One is a lithium-ion cathode that was imaged by the guys at NREL, and one is some SOFC anode, which was imaged by the guys at NETL. And as you can see, they're pretty different. They're both from quite large open source data sets, which is why we chose them. And we trained our GAN to try and recreate this stuff. And here's a sort of small sample of some results, right? So the top 2 rows are the real data, and the bottom 2 rows are generated data. And by eye, I would like to argue that you can't really see the difference between the 2, okay? So, but that's not good enough, right? By eye, well, your eyes can be trained. So what about calculating a range of key metrics of interest? So working from left to right, we've got volume phase fractions, surface areas, relative diffusivities, triple phase boundary densities, and the blue is the real training data and the red is the fake generated data. And you can see we get a pretty good agreement across all categories. The key thing that we are missing out on, although we've made some good progress since this paper, is about diversity. So you can see that the whiskers in the box plot are a bit narrower for the fake data than for the real data. And that's quite a common problem in GANs, that they get a bit stuck on the ones that they like, and you have to force them to try and generate a more diverse set of examples. Here's the 2-point correlation function. So it's a function that says, go to a point in your microstructure, do this for every point, but go to a point, and as a function of distance away from where you currently are, count basically how many of the ones in that particular spherical radius are the same phase as you. So it's this correlation between what you are locally and what everyone else is a function of distance. And this tells you a lot about the nature of microstructure. And what you can see, without going into too much detail here, is that our fake stuff looks a hell of a lot like the real stuff. And that's another good indication that we've trained it successfully. So this slide really is just showing off, right? You saw how small the examples were before. We can make as big a sample as you want. And this, I think, is one of the really important or exciting contributions from this piece of work. So having trained this GAN, maybe on a region that was, you know, often your tomography data is not quite exactly the right shape, or the volume is not quite the right shape that you want for the simulations that you'd like to run. But maybe all the information is in there. Maybe all the statistical information about the nature of the microstructure is in there, but you haven't got exactly the right tomographic volume, or maybe you've got an error in one bit and you lost some data and you have to throw that bit away. But if you've got enough to train your GAN and you can reconstruct your key metrics, I can now generate you, or Andrea can now generate you, as large a volume you want, of any size, okay? So this is bigger than any tomography data set you've ever seen, because it's not tomography data, it's a generated sample using the GAN trained on tomography data. The next cool trick that we've built into the system is periodic boundary conditions. We can force the generator to make microstructure that things that are cropped off the left-hand side actually re-emerge on the right. And same with top and bottom and front and back. So this microstructure actually thinks it was made in a tiny little universe only as wide, full, and deep as itself. Why is that useful? Because when you want to run simulations on microstructure, let's say you want to go, well, actually, I'm sitting in microstructure right now. Let's say you're a battery and you would like to go from my right-hand side to my left-hand side, and you'd like to simulate going through here, okay, going through my screen. I hope you can see that. What boundary condition do you put on the top and the bottom, okay? And ultimately, if you're using real tomography data, you don't know what's about to happen next. And certainly the multiphysics model that you're employing can't say, oh, well, we'll just assume such and such. The assumption that you almost always make is no flux. Nothing can flow off the side. But that can have really devastating consequences for your representativity of your sample, because you end up chopping off small fragments of particles on the side. And as far as that mirror boundary is concerned, that is now just a very small shard particle. So your particle that you had a nice tomography of all this central region, now at the edges of your volume, you've got these very strange, unrepresentative shapes. And that will mess with the results, right? That will suggest that your battery might charge much faster than it would in reality. So you can just about see, to those who have looked at flux maps before, the top is with the boundaries. In all cases, this is the same microstructure, okay? These 6 are the same microstructure. And I put a matrix of them so you can see that what comes off the right appears on the left and what comes off the bottom appears on the top. I'm doing a conventional diffusion simulation from top to bottom. And in the top simulation, I've got conventional boundary conditions. There's a mirror here and a mirror here. But in the bottom one, I've got this periodic system turned on, which has now been implemented in tau factor. So you can run this yourself. And now you can see that the paths, which are particularly active for flux, they are different, okay? And so this one used to be not very bright, and it's now very bright indeed. Periodic boundary conditions are a very well-established trick in the simulation community, but they are, of course, difficult to do unless you've got periodic microstructure. It's all right if you've got atoms, and it's all right if you've got a regular geometry, but if you'd like to have something that really looks like battery geometry, but also has this opportunity to take advantage of periodic boundaries and therefore is more easily representative, our GAN can make you some microstructure that does that, which is, we think, pretty exciting. The process we're currently working on is the electrode optimization, and we'll have some very exciting results to share from that soon. But one of the things I'd like to sort of share as a public service announcement is this adversarial problem. So this is AlphaGo, or this is the game Go, which famously fell to a computer algorithm called AlphaGo in the past few years. And the way they trained the machine is to make it play itself at the game millions of times. Okay. One of the things that you find when you're trying to do in silico optimization is that your optimizer will very likely just find your assumptions. So your model will always contain assumptions and simplifications necessarily. So one of the things that you should avoid or should be very cautious of is, can be clarified by this example. If you say, well, I don't know, I'm making a fuel cell and gas transport doesn't matter, right? Because it's always, you know, the solid state diffusion is so much harder. But if in your model you turn gas transport off, then don't be surprised when the pores close. If you're modeling a battery and you say, oh, well, electronic conductivity is easy peasy compared to the ionic conductivity, so I'm not going to bother modeling it. That's mostly fine. But if you put that into an optimization algorithm, don't be surprised if all of your CBD disappears, right? Because there's no reason to have it there because your model said it doesn't do anything. And so your optimizer said, all right, we'll get rid of it. So we've bumped into a bunch of these over the past few years, and they're always fun. So during that process of optimization, be careful that the assumptions that you're making aren't just the obvious conclusions of your optimization process. Okay, so that brings me nicely in terms of metrics that tell the right story to the next paper. And this new paper is almost published. It's just got 3 nice reviews. So we're just about to reply to them. This is my lovely collaborator too, who's at the University of Picardy with Charles de Lecour and Anano. And we have been working out specifically which type of tortuosity factor is the most useful. So we've got another punchy title here, why the conventional tortuosity factor is not well suited for quantifying transport in porous lithium-ion battery electrodes and what to use instead. So as someone who's been working on tortuosity for 7 years, I'm as surprised as you are. So here is the 2 sort of conventional tortuosity type metrics that people often see. The top one, geometric tortuosity, is something about a ratio of path lengths through an obstacle-filled system. So the red line divided by the distance between the top and the bottom. Then there's the diffusive tortuosity factor, which is much more relevant to transport and says, solve the diffusion equation in this space and tell me how obstructed your flow was. And just occasionally, but almost never of relevance, there is a relationship between those 2 things. If your paths are nice capillary paths, then you can relate them, but usually not, certainly not in porous media. In this paper, we looked at 2 empirical methods for measuring tortuosity factors. This one, Dean Wheeler did a lot of work on, where you put your porous medium of interest, could be an electrode, could be a separator, you put it between 2 conductive foils, and then you build a concentration gradient, let it relax and measure it and work out how difficult it was to get through that pore system. And the other one is just having a conventional symmetrical cell with pores on both sides and extracting from your impedance spectra what the transport related obstruction to movement was based on both of the electrodes, i.e. the ones on either side of the separator. We've simulated both because the one on the left is basically the conventional tortuosity factor. The one on the right is a new type of simulation that we've implemented in tau factor, and I want to share with you why it's exciting. Look at these 4 microstructures, okay? We want to travel from the bottom, which is the separator, to the top, which is the current collector. But already you might be thinking, why do you want to travel all the way from the bottom to the top? That's not how batteries work. You come in from the separator and you're not trying to get to the top. You're trying to get into the nearest piece of active material. That's where you're trying to get. But the conventional tortuosity factor says, how easy is it to get all the way through, all the way to the current collector? So it's not, you can already tell it's not quite the thing we were looking for. So what about these? Well, these have got a really nice property and 2 Tu and I drew these together, really interesting stuff. The three that aren't the first one, as it were, so the 2, 3, and 4, B, C, and D, all have the same volume fraction. They are all just modifications of A. And they've all got different resulting interfacial areas. The black is the pore, the white we could say is active material. If we use the conventional tortuosity factor, okay, actually B, C, and D, because we designed them that way, all have the same tortuosity factor. And because of how the Mullen number is calculated, which you can see in the top right, actually all 4 have got an identical McMullen number, which is very satisfying indeed. So all that's describing is, considering how much volume fraction of pore you've got, how easy is it to get from bottom to top? And the really exciting thing is, using our method, it's not trying to get from bottom to top, it's trying to get from the bottom, the separator, to the surface of the nearest white region based on conduction, so sort of Nernstian stuff, as well as capacity at the surface. So each bit of surface can only host so many things coming in from the outside. So we actually calculate an impedance spectrum, and then we use some analytics to extract from that with a fit what that would suggest about the tortuosity of the system. And what you can see is initially, A, B, C, and D are all uniformly bad according to the normal tortuosity factor, but that hasn't told us how easy it was to access the active materials. Whereas the bottom line, or the penultimate line, says, actually, some of these are much harder to access active material than others, and that needs to be taken into account. So you'd always normalize as well by the available surface area. And here's what the impedance box looked like. So to skip to a more realistic example, and one that comes up in papers quite a lot, what happens if you've got a slightly less porous region in your porous microstructure? And this is just a dropped spheres type microstructure, right? A bunch of spheres artificially rammed together. As you would hopefully suspect, the normal tortuosity factor, the diffusive tortuosity factor, cannot tell which direction you're going. I.e., it doesn't matter whether the dense bit is near the top or near the bottom, it gives you the same number, because it's saying how easy is it to get all the way through the microstructure. But with our method now, where it's how easy it is to get from one surface to the nearest region of active material on a capacitive surface, it really matters a lot. So if you've got a very low porosity region right next to the separator, your impedance is much worse, as you'd expect, as we have actually seen in real batteries, right? And if you've got a quite dense region all the way up at the current collector, but nice and porous before then, great, nice and easy transport, easy to access all the places you want to go. And this we are really excited about, because this hopefully will be one of those key metrics that enables us to do some of the in-the-loop optimization of microstructure, where we can say, this metric should really correspond to things that will actually affect performance in a real cell. And so you can hopefully see that each of these potentially seemingly a bit disparate pieces of work are actually coming together towards a process of in silico optimization with metrics that really resemble things that are actually relevant for batteries. I think the other thing that I meant to mention with optimization is, if you just tell it, oh, please maximize surface area, because that will improve your kinetics, or, well, then it's just going to make shards, tiny little particles. You want to give it actual constraints that stop it from making non-physical electrodes. And that's something else that our generator can do, because it will look at that and say, that doesn't look like an electrode at all. So we are constraining our system to electrodes that still look like the real deal. So that's it for those 2 papers. I'll just quickly summarize the tips that I mentioned before. So organize things, meetings, seminars, conferences, whatever. Teach as much as you can, not just for other people, but because it helps you actually learn things. Write software, not code. Make sure other people can use the things that you spent so much time and passion constructing. Publish your software so that it can actually get out there in the world. And I think more importantly than any of the rest, tell people about your work. They want to know, right? If I'm working on a thing and you think you've found something really interesting about microstructure or GANs or tortuosity, get in touch, drop me an email. I'd be delighted to hear from you. So with that, I'd like to thank my team. They're all wonderful. So you saw some of Andrea's work. Liam and Steve and Charlie are relatively new to the department. But Liam is working on the characterization of solid-solid interfaces in fuel cells. Steve's a Faraday-sponsored PhD, also looking at machine learning for microstructure. And Charlie Wood is doing some great stuff around 3D imaging of carbon paper electrodes. This is the wider team, most of the electrochemical science and engineering group, many of whom are sponsored by the Faraday Institution with our new flashy logo. And just to mention a few people who are missing, Ainara and Rowena and Nina have been doing some painstaking work around characterizing transport processes in cathode materials and solid-state electrolytes, and I'm constantly amazed by their patience. Greg and Jacqueline, who've been holding together the multi-scale modeling project. Donal and Francois over in NREL, who've done some great stuff around transport and microstructure and imaging. And of course, not to forget the Twitterati, Dave and Steve and Seifel and Electrochemical, who is of course Edwin Koo in disguise. These, it's been so great, especially after Dave's initial kickoff conference. I knew he was very disappointed that the Oxford Battery Modeling Conference had to be postponed, but it turned out to be a roaring success online, and it's been great interacting with everyone via Twitter since then. So with that, I'd like to thank you very much for your time, and I'd be happy to take any questions.
Thank you, Sam. That was really interesting. So yeah, we've got about 10 minutes to take some questions. I'll start with Chuang Cheng. I think this is on the periodic boundaries slide. And they're asking, why is the binder, the white bit, only attached to the NMC, but not inside the carbon, the black?
Very fair question, and I can give you a very unfair answer, which is ask Donal. So we took open source data sets and we trained our GAN off that. We can train our GAN off any data sets, but we just picked this one. The reason it is the way it is in his data is because it's very difficult to image. And I think a lot of progress has been made over at UCL about how to take that to the next level and do it a bit better. But I think in Donal's data sets, they tried a range of different thresholds and we just picked one of them arbitrarily from the website. So our microstructure is only real in the sense that it really looks like whatever the training set was, and not because we really think that's exactly what the microstructure looks like.
Thanks. And a question from Seifel. So it says, yeah, excellent talk, Sam. So related to the slide before the Go slide, talk about diffusion. Can you derive quantitative data on rate capability and or diffusion coefficients? Do they compare well with experiments?
The slide before the Go slide.
Yeah.
This is the, well, the answer is we don't know, because this is the painstaking work that Ainara, Nina, and Rowena have been mostly pursuing. And it's still very difficult to extract exactly what's going on, because these materials are so reluctant to exchange. So we're using a lot of isotopic techniques. I mean, I hadn't talked about that in the presentation, but Liam and Ainara and Rowena and Nina are all using these isotopic exchange-based techniques. And yeah, saying it was harder than we thought is perhaps sounding a bit naive, but like it's a lot harder than I thought. But maybe that's because I'm not an experimentalist. So I hopefully will be able to get back to you, Seifel, with an answer in a few months' time, but it is really difficult.
Cool. And then question from someone, anonymous attendee. So they say you need to make consumptions and assumptions when building the model and later run the simulation. Is there any chance that these assumptions cause artifacts and mislead the conclusions?
Yeah, absolutely. And I think I touched a bit on that. Maybe that came before my slide, but I think, you know, as soon as you progress to the space of saying, oh, well, now we're going to sort of throw it in the black box optimizer and trust what comes out the end. Well, you can be actually quite confident that what comes out the end will be nonsense, because we definitely don't resolve all the physics in our models. You know, even in a 1D model, we choose to ignore a lot of physics, but in a 3D model, we choose to ignore most of the physics because it's just too computationally heavy. So yeah, I mean, there's absolutely a risk of that. And one of the ways that you manage that is by placing constraints. So you do a sort of constrained optimization where you say, you're just not allowed to go to these silly regions of the space. because they don't mean anything. So yeah, absolutely, you need to be really careful with that.
Cool. And then another question, say, great talk again, thanks Sam. Have you thought about liquid flow through porous media? How do you think tortuosity factor correlates with flow battery performance?
So yeah, we are looking at that a bit now. Ultimately, actual flow, like fluid flow, is rather more complicated affair because you've got all these sort of viscosity things going on as well. But my guess would be that still, if your system is controlled by flow, that you're probably still going to have some relationship to a tortuous type event. But I suspect if you want to know what's really going on, you'd have to actually solve Navier-Stokes, which is, you know, no one wants to do that. So yeah, I suspect there is some relationship, but I think if flow is important, you probably have to simulate flow, which tortuosity factor does not.
Okay, and then Ankit says, please elaborate on the restricted diffusion method by Dean Wheeler. Is it not an experimental approach? I think I got confused because of the term empirical.
Yes, so we talk about it in great detail in the paper. There's quite a lot of things to say about it, but the broad idea being a couple of lithium sheets, one on each side, some kind of separator or buffer to make sure they don't touch electronically with whatever is in the middle, and then a piece of porous media, whatever you want. It is an experimental technique, and you pass a current through it until you've set up a concentration gradient across the system, and then you get rid of your potential difference, and you see that thing relax back, and you can extract from that the diffusive behavior of the system, and that hopefully should resemble quite the conventional tortuosity effect.
Cool. And then from Zufei, very good presentation. So they say, if we use metal foam, i.e. the nickel foam, as a 3D current collector in the electrode, do you think it will make difference in pore structure and the diffusion behavior?
I suppose it will make a difference because it will be a different system. Not a very helpful answer for you. I know that some there's the Prieto cell, I think it's a Canadian group, have made a cell where they start from a very low density porous current collector, and then they do a sequence of dip coatings and make a sort of dense 3D battery, you know, so it's not got layers. The whole thing is just a block of cell. I think one of the interesting things with playing with your current collector is that your current collector is already usually very overspecified in terms of your electrochemistry, i.e. there's plenty of space for electrons to move on space. There's more metal than you need. The metal is there because making it any thinner is mechanically irritating during your manufacturing processes. So in my opinion, doing lots of things to try and play with your current collector is probably solving a problem that you often don't have, which is that the electrons can't get where they need to be. You do have that in some scenarios, but you often, the electrons can be mostly ignored.
Okay, I will take two more questions. So someone says, experimentally, we are working on modifying carbon surface for improving its electrode performance. Experimentally, using impedance and cyclic voltammetry, we are analyzing pores, the roles and active surface area. Can you please suggest to us some courses or books or papers to start to simulate battery performance for electrodes?
Yeah, I can. I mean, and I can send you an email about it as well. There isn't a huge amount of online content around actual battery modeling, and I think this is something that the Faraday Institution would actually like to resolve. So there's some sort of high-level BMS control theory stuff, which is really nice. But if you want to actually model at the electrode scale, there's much less. Yeah, but you're welcome to drop me an email. I can drop a whole bunch of links to some of my favorite talks and content.
Yeah, okay, and then maybe one final question. so this goes back to, like, I guess your career things. So how do you communicate with your team to make sure everyone can do their best in his or her specialized field?
I have found management super difficult. I mean, it's so tough, and you basically don't get any training for it. And you know, if you can publish a bunch of papers and teach, presumably you can manage. I'm not sure if that's particularly related. You know, I think in academia in general, there's a lot of strange stuff that's like very decorrelated. Like, for, you know, the classic one being that if someone's really good at electrochemistry, it does not mean they can teach electrochemistry. In fact, they might be very bad at teaching electrochemistry. With my team, actually, my approach has just been evolving constantly. And although it's slightly awkward to do, I think they're used to it now, which is that I ask them how they think I'm doing. And so we will have quite regular discussions about management structure. Obviously, we're living in weird times, so we actually meet every single day as a whole team. And we used to meet every morning during the early stages, and we've switched now because we all want to just get on with our work. And we meet every day at 5 just for a coffee and a chat. And we also then all meet one-on-one, as it were. And I do my best. I think you can probably tell from the talk, I'm someone who, if you let me, will just talk non-stop. So I'm doing my best to try and listen more. And I think, you know, PhD students spend, you know, 50 times more hours per week thinking about their project than their supervisor. Or maybe that's a bit of an exaggeration, but at least 20 times, right? So they've probably had more interesting thoughts about their project than you have in that time. So yeah, I'm trying to make more of an effort to really extract all of that detail from them by listening more. But it is really tough. But I think, yeah, creating that environment, I felt like I often had opportunities available to me from Nigel and John, and they just say, yeah, go and do whatever. And so I did. And it's finding that interesting balance, which is still, I think, quite tough, where you want to encourage people to do whatever they want to do, but sometimes you also want to push them a little bit to go and do something that they weren't super keen on, like organize a conference or a meeting, because you hope that they would benefit from that experience. But it's not always, you can't always say that with great confidence. You just have to cross your fingers.
Right. Yeah, thanks a lot, Sam. I think that brings us to the end of this webinar. Thank you all for attending. I think, yeah, at some point we had 204 attendees.
Wow.
Yeah. So, yeah, thank you, Sam, for doing this, and stay tuned for announcement for the next webinar.
Great stuff. Thank you so much, Rema, for inviting. Thank you all so much for your time and taking time to listen. Please get in touch. If you've done some interesting work, send it to me. I'd love to read about it.
Yeah, and yeah, hopefully we'll have the video out sometime soon.
Lovely. Okay, take care.
Bye-bye.
Bye-bye.